Konnichiwa, JSConf Japan. So, may I request all of you to please stand up? We'll just do a small warm up to freshen up ourselves. Put your hands up like this. Hands up? Yeah. On my count of 1, 2, and 3. 1, 2, 3. Maybe you can count in Japanese. 4, 5. We are close. 6, 7, 8. We are very close. 9. And here goes the last one. 10. Awesome. Thank you so much. So I'm very excited to be back at JSConf Japan, and today I'm going to talk about web crypto APIs and how can you use them to encrypt the data in the browser, and how can this help you to enhance the security of overall security of your web applications. So before I dive into my talk, let me quickly introduce myself. So I am Aakansha. I am an associate, one of the co-maintainers of Excalibur, React Tags, Mermaid Excalibur, and a couple of more libraries. And these are my socials. I would love to connect with all of you. If you want to talk about front-end, JavaScript, open source, canvas, security, I'm all in for that. So yeah, let's connect. And let's get started with the topic. So what is encryption and decryption in simple words? So you take a plain text, lock it with some key, and you get some gibberish text which is unreadable. That is ciphertext. Now you take a ciphertext, unlock it with some key, and you get back the original plain text. That is decryption. Now broadly, there are two categories of encryption. The first one is symmetric encryption, where you can see Alice and Bob, they have the same key which they are using to encrypt and decrypt the data. Now, since it's the same key, so it has to be a secret key, you cannot share it with the entire world. This is symmetric encryption. And the next one is asymmetric encryption, where Alice and Bob have a pair of cryptographical keys. One of them is a public key, which is available to the entire world, and the other one is a private key. So Alice is using Bob's public key to encrypt the data, whereas Bob is using his own private key to decrypt the data. Now let's look at a traditional client-server architecture when we build our web applications. What happens when there is an exchange of data between client and server? So whenever there is a exchange of data in the network, in the transit, the data is encrypted with the help of HTTPS or TLS. But if you notice, we are storing the data in raw format in the server. Now what if tomorrow your server gets compromised or gets breached? The data could get breached because you are storing it in raw format. So is there any way we can avoid this? Let's look at that. So how about this model? Well, instead of relying on HTTPS to encrypt the data, we encrypt the data first on the client and send the same encrypted data over the network and store the same encrypted data in the server as well. This way, even if tomorrow the server gets compromised, the data is still secure because the data is encrypted. And this can actually give you the maximum amount of security, because if there is an exchange of data between me and you, there is no one in between who has access to the data, not even the server. So this is basically give you the maximum amount of security. Now, to encrypt the data and the client, we have something called web crypto APIs. And web crypto APIs have been there for quite some time, and their support has evolved over time. As you can see, it has great support over majority of the web browsers, and it's also supported in node.js. So it's like write once and run everywhere. You don't need to install a second module for node. The same API, the same code, you can use it in the node as well. Now, vendor of crypto module is divided broadly into three categories: get random values for generating randomized values, random UUID for generating unique IDs, and crypto.settle is the main API which I'm going to cover in. Now, the API is named settle because this crypto.settle has some strict requirements which you need to fulfill to get the maximum security out of it. And all these APIs are available in a secure mode. By secure mode, I mean HTTPS. But only the get random values is available in non-secure mode as well. So we already have map get random. Then why do we need get random values? Now I had this curiosity. Has anyone of you come across this particular info in the ambient docs, which says that you should not use mat.random because it doesn't give you cryptographically secure values. Now I agree with it, but I had this curiosity that why? Mat.random, the numbers does sound random to me, so why is it not secure when it comes to cryptography? So I did it a bit, and I came across this interesting article, which is a very old article, as you can see. It's a 2016 article, and in 2016 there was this powerful jackpot worth 1.5 billion dollars, and for this to create an environment, an excitement, Los Angeles Times released a simulator. It's still live. You can actually check it out, where you basically need to guess the numbers and you win the prize. Now Douglas Goddard, he actually wrote this blog and he dig into a bit more if he can guess those numbers. And in digging in, he came across this. So this is the V8 engine source code, and it's a random number generator. And this is how the random number generator works in the V8 engine. So it uses XOR shift 128 algorithm, which is basically nothing but a mix of XOR and shift operators, bitwise shift operators. But the thing to note, it's a CPP code. We are not going to dive into this, don't worry. But the thing to notice, it depends only on these two state variables. And if by some way we can guess these two state variables, then we can actually guess the random numbers, because as you can see in the code, the numbers are guessable. And by some interpolation, just imagine it as a math equation where you need to solve x and y by by interpolating it with some values so that you can guess the future values. And for this, let me actually show you a quick demo. This is a Python script which Douglas Goddard has shared in the same article. I have just modified it a bit, and you can actually find the script there as well. So let's try this out. I hope it's visible. Now I'm going to generate 5 random numbers in the browser. So these are my random numbers, as you can see. Now I'll be copying the first 5 random numbers because I need some initial value, some initial input to the script. So I'm going to copy these numbers and see how if it works. So now you can see these are the state variables which the script is predicting, and these are the next random numbers. Now let me see what are the next random numbers generated. Okay, I hope the numbers are visible there. But if you notice, 0.5281664890237. It's present here. 0.5281664890233. Okay. The next number is 0.002059933. 0.0205933. It's also present. 0.95827918. 0.95827918. That's also present. 0.24452493. 0.24452493. It's present. So this, I really love this article because it resolved my curiosity, and I understood that okay, math.random numbers are actually guessable, and that's the reason you should not be using it when dealing with cryptography. And yeah, if you want to deep dive, I would highly recommend to read this article. So with this, let's go back, and I have a quick performance demo just to make you understand what is the performance difference between these two APIs as well. So let's do it for 10,000 numbers. So when running for 10,000 numbers, math.random is taking 1.6 millisecond, whereas get_random value is taking 23.8 milliseconds, which it's like a good difference. And if I run it for 100 elements, then it's 13 millisecond versus 105 milliseconds. So math.random is pretty fast than get_random values. The reason being the entropy is very high for get_random values. That's the reason you are not able to guess the numbers as well. So depending on the use case, decide which one you should be using. It should not be like you just prefer one over the other for no specific reason. So if you are, let's say, generating some hex code for your colors, go with mat.random. But if there is any reason for the security, you are generating security specific code, go with crypto.get_random values. So let's go to the slides. So let's understand crypto.subtly. Let's have a generic overview of this API. It's only available in HTTPS, as I mentioned earlier. It has generic APIs, which means you don't have different APIs for different algorithms. Rather, the API stays the same. What differs is the algorithm parameters. So different algorithm will have different parameters, but the API will remain the same. It deals with only binary data. So the input and output of the crypto.study API is always going to be binary data. And we are going to deal a lot with binary data in the future slides. All the APIs return promises, so we are going to use the same return as well. Now these are the crypto.study APIs which you can get in the docs as well. I'm going to cover encrypt, decrypt, generate key, derive key, encode key, and export key in my talk. Now, as I mentioned that we are going to deal a lot with binary data. So for that, we have something called typed arrays, which helps you to interact with the binary data in the browser. Typed arrays is not really an array. These are basically array like we use it to binary data, which helps you to interact with binary data right from the browser and manipulate them. So these are the basically types arrays which are supported. We are going to go ahead with UV data array because it covers the majority of the use case, especially because we are going to deal with the text, and UV data array works for that. So U basically stands for unsigned. Unsigned means you can only store positive numbers. Int is integer. The range will be 0 to 55, which is for integer. 8 is the size of each number in this array is going to be 8 bits, and it's a typed array. So let's consider a stream of bytes. Now what happens internally is it gets divided into 8-bit segments. Each 8-bit segment is converted to its equivalent decimal, and this is what you see in the browser. So this is when you log the event data, this is what you will be seeing. So this is what an event array is, and now how do you use it? So there are many ways to use it. You can initialize it with some arbitrary length and it will be filled with zeros. You can initialize it with some values and it will be initialized with those values. You can represent string using the text encoder.encode API, and that will also give you the bytes. And it works for emojis as well. So it pretty much covers a lot of use cases. So now, before actually finalizing an encryption algorithm, there are some minimum criteria which we definitely need to fulfill before going ahead with any encryption algorithm. So let's look ahead, let's look at those minimum criteria. The first one is confidentiality. So when I'm sharing some data with you, only me and you should have access to the key with which you can interpret the data, and no one else in this room should have access to it. That is confidentiality. Integrity. When I'm sharing some data with you, when you receive the data, you should be able to verify whether the data was manipulated. If the data was manipulated, you should be aware of it. You should be able to identify it. So integrity is something which you should be able to verify on your end. Authenticity. When I am sharing some data with you, you should be able to verify whether it's really me who sent you the data or someone else. So these three are the minimum criteria which we need to fulfill. Now let's look at the encryption algorithms which are supported. So these are the algorithms which are supported. RSA is an asymmetric key algorithm, whereas AES is a symmetric key algorithm. So I'm going to cover AES in my talk, and there are these three different modes when it comes to AES. AES basically stands for Advanced Encryption Standard, and this counter mode, blockchain, and Galois counter. So let me show you a quick demo so that you can understand what is the difference between the various modes and which one you should be picking. So let's go to the demo. Okay. So let me type some text. See, I am super excited to be back at JSConf Japan. Okay, and let me encrypt it. So now this is the output which you get. It's in bytes, and I am using this, and I am actually using the counter mode right now. So let me copy this and try to decrypt it. So it works fine. It looks good. Now let me manipulate the bytes. Let's say some eavesdropping happened, and I manipulate these bytes. Then you notice that AM changed to AL. If you didn't, let me manipulate it more. Now I think it should be clear that there is a creator sign available there. So basically, when you receive this data, you will think that I have sent you this data, but I did not send you this data, right? So you are basically not able to verify the integrity of this data. And that's why we cannot go ahead with the counter mode, because there is no way for you to identify whether the data is actual data or the data was manipulated. This data is actually manipulated. So let's try the other mode, which is the CBC mode, the blockchain mode. And let me see what happens when I try to decrypt this data. This is using the blockchain. This is fine. Now let me manipulate it. Okay. Again, some of the bytes are invisible, but rest of the bytes are visible. So when you receive this data, you will still think that Aakansha has sent you this data, but I did not send you this data. There is some eavesdropping happening, and the bytes were manipulated. So again, this also you are not able to verify the integrity. Now let me try out the GCM and see if that helps us. So this is the GCM mode, and now let me try to manipulate the bytes here. This failed. This is what you want. So when you receive the data, and if there is some manipulation, some tampering of the data, you will realize that when you receive it, because the operation just fails. And that's what we want. You should be able to verify the integrity of the data, and so as the authentication as well. Both of them actually go in parallel. So that is the reason GCM is the recommended one, because it comes with integrity and authentication. So with this, we can say every algorithm comes with confidentiality as long as you are not sharing the keys with someone else. So counter mode and blockchain mode gives you the confidentiality but not integrity and authenticity. But GCM mode gives you confidentiality, integrity as well as authenticity as well. So with this, GCM internally uses the counter mode, but it also adds a 16-byte authentication tag, which helps you to verify the integrity and authenticity. So whenever there is a tampering of data, this authentication tag actually gets impacted, and that's why the operation fails. So with this, we will be going ahead with AES GCM mode for finalizing the encryption algorithm. Now there are a couple of things which we need to understand before diving into web crypto APIs. The first one is the crypto key. What exactly is a crypto key? So crypto key is nothing but an opaque representation of a cryptographical key. When I say opaque, it means you cannot view the bytes of the crypto key. Even if you are the developer who has generated it, you cannot view the bytes of the crypto key. All you have access to is these four parameters, which is the type of the crypto key, whether it's a secret key or public key. What algorithm have you used to generate that crypto key? What is the usage? For what purpose have you generated this crypto key? Is it encryption, decryption, signing, verification? What is the purpose? This is an interesting and my favorite. So, as I mentioned, you cannot view the bytes of the crypto key, but when generating the crypto key, you can say that I do want to extract the bytes of the crypto key later because I have some things to do. And for that, you have to set this parameter to true. Then only you can extract the bytes later. By default, it is false. So yeah, if you have to extract the bytes later for some purpose, make sure to set this parameter as true. So that's about the crypto. Now let's go ahead with AES GCM 128 encryption algorithm. 128 is basically the length of the crypto key, which is 16 bytes, and it also needs an IV. IV is initialization vector. It's basically a set of random numbers, nothing else. Initialization vector is just a fancy name, but it's just a set of random numbers which we need to generate. And the minimum recommended length of an IV should be 12 bytes. You can go more, but don't go beyond, like less than 12 bytes. So these are parameters AES GCM needs. Now let's have a quick demo of just to understand the visualization of how AES GCM 128 works. So I have this quick demo. So let's first try to generate a crypto key. Now the parameters look good. Algorithm and user and everything is set correct. Let me try to break it. Okay, it's breaking there, but I think there's some resolution issue. So it says that it failed to export the key because extractively set to false. I need to set it to true, then only I can view the bytes. So let me actually set it to true, and now let me generate the crypto key again. and view it. Now I am actually able to view the crypto. What internally happens, I'll be diving into that, but for now, I want to show you that when you set the extract parameter to true, you can actually view the bytes of the crypto key with the help of some APIs which the crypto APIs give us. So this is the basically the exported format of the crypto key. Let's call this encryption key. And let me have some text here. So let's say JS Japan. Awesome. Now this is the output in bytes which you are seeing. All the output will be in bytes. This is the data in bytes. This is the conversion. And when I encrypt it, this is the output, and this is the ID. Now notice here, when I click on encrypt again and again, the output is changing, if you notice, and so is the ID, but the text remains the same. And this actually creates an illusion to the outer world because they'll think that the output is changing, which means the input is also changing. But in reality, the input still remains the same. So this is possible because of this IV. IV basically adds randomness to the output. It randomizes your output, and this way it makes it more stronger and harder to decrypt. And that's why you should never reuse the same ID for encryption. For every encryption, regenerate your ID so that the output is randomized. That is the purpose of IV. If you use the same IV, then the randomness is lost and you really don't get the benefit out of it. So now let me, copy this output and try to decrypt the data here. And I need the encryption key. So let me copy this as well. I cannot copy the crypto key, so I need to export the bytes and copy the encryption key. And now let me copy the ID as well. Okay, so now this operation failed. I just copied the parameters. Can someone tell me if I did anything wrong? Why did the operation fail? Because if you notice, I actually changed the ID. I tweaked the ID. So let me change it back. And now it works. So basically, the thing to note here is that when decrypting the data, the along with the encryption, along with the encrypted content and the encryption key, you also need the exact same ID. If you tweak the ID, it is going to fail. So let's make a note of it that you need the exact same ID with which the data was encrypted. Now let's go back to the slides. And yeah, let's build a note-taking app. So we want to make it end-to-end encrypted, and we want the ability to share the notes so that I can share a link with you and you can actually go ahead and access my notes. So let's take a look at how we are going to encrypt the data. So this is the encrypt API. It basically needs the algorithm parameters, which is the name and the ID for AES GCM. It needs a crypto key. Every algorithm needs a crypto key, and it needs the node but in bytes because the input and output of all these scripted APIs is going to be in bytes. So let's look at how you create an IV. IV is nothing but a random set of numbers, that's it. So it's pretty simple to create. Just initialize a unit array with 12 bytes. It gets filled with zeros, and then just fill it with get random values because we are dealing with security. We don't want anyone to guess my ID. That's why we use the get random values. And that's it. You create an ID and you are ready to use this. Now, crypto key, you know what a crypto key is and how it looks like, but how do you generate it? So we have an API for that. You basically use this API crypto.generate key, and it has the algorithm parameters which it needs, which is basically the name of the algorithm and the length of the crypto key. Now, extract table I need to set it to true because when I share the link of my notes with you, I want you to decrypt the data. So I need to extract the bytes of the crypto key later. I'll show how. But for now, let's set it to true. And it's going to be used for encryption and decryption. So with this, as soon as the promise is resolved, you will get the crypto key. Now, this is how the crypto key looks like. Exactly similar to what I showed you a couple of minutes back. It has the algorithm parameters, the extractable parameter is set to true because I need to extract the bytes, and the type is secret. So everything looks good. Now the last is the notes but in bytes. So that's also simple to do. it's a string, so just use the text and encode API, convert it into bytes, and you are ready to go with encrypting the data. As soon as the prompt is resolved, you will get the encrypted buffer. So now, as I mentioned some time back in the demo, that I can just go ahead and load this encrypted buffer to the server so that you at your end can fetch the data. But you also need the ID to decrypt the data successfully, right? And IV is not something which I want to really hide from the entire world, because I am going to regenerate the IV for every encryption. So it's not something which I want to hide it from the entire world. It's a one-time use. So I can actually upload the IV along with the encrypted buffer to the server as well, so that when you fetch the data at your end, you get the encrypted data which I had uploaded, and also along with that you get the IV. So the first 12 bytes of my payload is going to be IV, and the rest is encrypted data. So let me just go ahead and upload this to the server. And once it is uploaded, you will also have the access to the data. So now what is left is, you still need the encryption key, right? Without which you cannot decrypt the data. So, and for that I need to export the bytes. That's the reason I set the extractable parameter to true. But how do I share the crypto keys securely so that no one else in this room will have access to the crypto keys? So for that, let's look at this link. It has it's basically a normal URL. It has a scheme, it has a domain, it has a path, it has a file, and it has a fragment. We as software developers, you often use this fragment. Where do we use it? Any guesses how often do you use it, and where do we use it as developers? Sorry? So I'm not able to hear. Encore. Okay, so what I was going to refer to is we all use GitHub, and it's also used in the GitHub Markdown for navigation, and that's where you use this hash a lot just to navigate. Now, is this sent to the server? It's never sent to the server, right? And we can take advantage of this behavior. We can actually store the encryption key right after the hash and share the URL. So when I share this URL with you, only you will have access to the encryption key. No one else, not even the server, because that key is never sent to the server. So with this, I can actually go ahead and share the URL. But there are some exported formats which are supported with the Web Crypto APIs. These are the supported formats, and we are not going to dive into all these formats. But let's have a quick overview of where these formats are supported and for which algorithm it works. So these are basically raw, PKCS8, SPKI, and JWK. So this is the quick overview of which format is supported for which algorithm. So raw format works for AES, HMAC, and electrical public keys. PKCS8 works for RSA and electrical private keys. SPPI works for RSA and RSA public and electrical public keys, whereas JWK works for all. So JWK is something, if I change the algorithm tomorrow as well, I can still use the JWK because it is supported for all the formats. It's supported for all the algorithms. Now, JWK basically stands for JSON Web Key, and this is how it looks like. It's basically a JSON, and you have these parameters. And what I'm interested in is the K parameter. That is my encryption key. This is what I'm actually going to share with you in the URL. And now with this, we have the export key API, which basically you pass in the format, which is JWK, and you pass in the crypto key, and then I can get this encryption key, and then the next step would be just to create the URL and share it. So in the URL, I'll be also sharing the nodes ID. Let's assume that it's some ID which you use to fetch the nodes from the backend, and the next one is the encryption. So with this is the URL which I'm going to share with you. Now, when you receive this URL, the first thing which you do is, fetch the data from the backend. So when you fetch the data from the backend, these are the two attributes which you have. You have the nodes ID, so you can fetch the data from the backend, and you have the encryption key in the URL as well, right? So let's just fetch the data from the backend, and this is the decrypt API. It is exactly same as the encrypt API. It meets the exact same parameters. it needs the name of the algorithm, it needs the original ID with which I have encrypted the data, it needs the original crypto key with which I have encrypted the data, and the encrypted content. Now these two things are already available, right? It's already available in the payload because I just uploaded the encrypted buffer along with the ID so that you can have access to it. So let's just get it from the backend and let's get the ID. The first 12 bytes are going to be the ID and the rest is the encrypted buffer. So these two things are done. What I'm left is with crypto. Now, what I shared with you was the exported format of the crypto. That is the encryption. I used the export key API and I shared the encryption key with you. But this API is compatible with the crypto. So we just need to do the reverse engineering and go back to the crypto key format so that it works with this API. So what we do is we just add the missing attributes. This was the K attribute if you remember. We just add the missing attributes and convert it to this JWK format so that it looks like the JWK format. In this case, if you notice, extractable parameter is set to false because now I don't need to extract the bytes anymore once the decryption is done, and the operation is just decrypt. And similar to export key API, you have the import key API which you can use to convert an exportable format to the crypto key. So that's what you use. You just pass in the crypto key, or you just pass in the exported format, which is JWK, to the import key API, and it gives you back the crypto key. So now you have the crypto key. So just go ahead and decrypt the data. And once the promise is resolved, you will have the decrypted data, and you will just run the text decoder.encode API to actually convert it to the original plain text. Now this is done. Now the end-to-end encryption works. I'm able to share the data with you, and you are able to access it with the end-to-end encryption which we just implemented. What if the last step? What about adding a password protection layer on top of it? So if someone has access to your machine, they still cannot access your nodes unless and until you know the password. So by this I mean is, let's generate a crypto key from a user-generated password. So for that, let's understand hashing. So by what is hashing? This is let's consider SHA-256, and you have a string. You get a fixed output of bytes. If you change the string, you again get a fixed output. If it's a multi-line string, still the output is going to be a fixed length. It's not going to vary whatever the length of whatever the input is. But this process is irreversible. That's how we store the passwords in data, right? We use hashing. And this is what we are going to use. And along with this, there is this algorithm called PBKDF2, password based key derivation function. What this does is it basically helps you to generate a crypto key from a user generated password. And this is how it is going to work. So you take a user generated password, feed into PBKDF2 along with SHA-256, add some salt to it. Salt is nothing but similar to I just a random set of numbers. Iterate this at least 100k times. This is the minimum value recommended. You should at least iterate this whole process 100k times, and then you end up generating a strong cryptography. And in this case, we are using AES-GCM for the generating the cryptography. So when it comes to the code, it's like this entire thing can be taken care by the derived key API, derived key, and when it comes to the code, it looks like some sort of this. So you need to pass the algorithms to generate the base crypto key, which is PBKDF2. You need to pass the base crypto key, which is being generated from your user-generated password. Basically, you are converting the user-generated password to crypto key, which with the 2 bytes with the help of import key API, and derive the algorithm, and the rest of the parameters are same as you use for generating the. This is how it looks like. So this is the algorithm which we are going to use, and this is the password crypto key, base crypto key. These are the derived key algorithms, the extractable parameters, and the usage. And once the prompt is resolved, you get the crypto key. So I just have a side project which I had built as a result of learning the web crypto API, so I'll show that. So this is basically, let's say I have some string. It basically uses AES-256 and PBKDF2 to generate the password, generate the crypto key from the password. So let's say I have a string I love Japan, and I enter some password and I encrypt it. So instead of those boarding bytes, you actually see the emojis and you can actually play with the theme here. And since I'm giving this talk in Japan, so I added this kanji theme. So emoji is my favorite. So let me just copy this and type the password here, and that's it. You decrypt the data. So it's open source. You can actually check it out. And yeah, with this, let's just wrap up with the takeaways. So we learned about different types of encryption, symmetric and asymmetric. Web crypto APIs have good support in majority of the browsers and Node.js as well. Type values to deal with binary data. Crypto.get random values to generate the randomized numbers. Various alias modes and alias GCM is recommended as it provides integrity and authenticity. Cryptography for encryption and decryption in browsers. Usage of fragment in URLs to share the keys. Various export key formats and usages. PVPDF2 for deriving the crypto key from password. But the thing to remember here is that the algorithm can be slower. The more the number of iterations, the more the stronger the crypto key will be. And yeah, the one question to you all is, can you add into your encryption in your app or pass with your app? Let's discuss this. I would love to know. And these are some amazing encryption talks which I would highly recommend if you are interested in diving into encryption. I really love these talks. And yeah, these are my resources. All the resources are shared in this QR code. So you can scan this, all the projects and whichever I showed you. Everything is available here. And that's it. I am doing this Canvas workshop in January. So if this is something which interests you, you can actually check it out. And that's it, Ariya Gozaimasu. Thank you so much. And thanks to Yusuke for helping me with the Japanese translations. So yeah, thank you for having me.